So today we have two talks. The first talk will be the continuation of previous talk by Artem and Sobolev about computing stochastic gradients and stochastic computational graphs. And then there'll be Alexey Umnov with a talk about alpha GANs, and maybe we have time about Bayesian GANs. So Artem, please.
Okay, so I'm the same guy presented last week. Let's first start with a quick recap of what we have learned so far. Very quick. Computational graphs are basically neural nets. Sometimes there is stochasticity in them, and we want to learn parameters of this stochasticity. The mathematical formulation looks like this. We'll only care about parameters governing this stochasticity. There are many applications already, and many more are to come with these advanced techniques that I have and will cover. There is general case, also known as the reinforce. However, it suffers some problems like big variance, and it doesn't use any information regarding the derivatives of f of some kind of the target function, the function we actually want to minimize. We want to minimize this expectation. Actually, in this talk today, we will focus on improving this reinforced estimator, and we'll try to use the derivative information about f. However, in some special cases, when reinforce does not work well, there are some other techniques. For example, you can actually backpropagate through random samples, and this is the formula for that. However, it's not easy to use in practice because, well, it requires you to be able to invert your your cumulative distribution functions for conditional marginals, and that might be quite messy. For some distributions like Gaussian, there is a natural reparameterization technique that allows you to re-express, to reparameterize your arbitrary Gaussian random variable as some deterministic transformation of independent random variable. In general, it can be formulated for many other random variables, however, not for all of them. For example, a huge point of interest are Dirichlet distributions, particularly Bethe distribution, and they do not allow such an efficient reparameterization. In that case, there's been some work on doing some kind of generalized reparameterization, where you represent your random variable of interest not as a deterministic transformation of something that's completely independent of your parameters, but something that only weakly depends. For example, it can depend on the parameters theta only via higher moments, third, fourth, and so on. And the first two that one might think are determining the most of what's going on in your computational graphs. These lower moments are fixed. Those do not depend on parameters theta. So as you can see here in this reparameterization, in this method, we actually use both the gradient information of our function, of our target function, to integrate and the log derivative and the square function estimator, also known as the reinforce one. There is some more mathematics about this method, but actually these two, the generalized reparameterization and the basic reparameterization trick, mostly cover the spectrum of working with continuous random variables. Of course, sometimes their variance is still high, and there are some works to reduce this variance. However, that seems to be working pretty well in practice. However, there was some example. However, for discrete random variables, there is no inherent notion of differential of the gradient because they are inherently discrete. So what we can do is to relax those and to make them continuous and hope that our approximation will be good enough. For example, in some very restricted cases, one can actually use the concentration behavior of discrete random variables to assume that their collective behavior is more like a continuous one. If you are working with dropout, you can see that your pre-activations are approximately normal, I mean in the limit of infinite amount of neurons, and you can replace the binary, the Bernoulli masks with Gaussian. That's why Gaussian dropout is kind of equivalent to binary dropout. Until last week there was no paper mentioning this method, but last week there was a ICLR deadline for the next year, and there was a paper proposing exactly this method for something like learning discrete weights in neural networks, I believe.
But we'll still not be able to optimize with respect to individual binary dropout rates, right?
We will. You just replace every binary dropout mask, every binary mask, yeah, with a Gaussian noise that is dependent on the. Well, basically, it will have the same moments as the corresponding binary random variable, and you can.
So you want to say that
minimize individual nodes.
Individual binary dropout rate. Then we use this kind of transformation and transform it to Gaussian noise. Then we're using local representation trick to fine-tune this Gaussian magnitude, and then we switch back to binary probability.
Yeah, at the test time you're using discrete random variables, and at the train time you use the continuous Gaussian random variables. Of course, it works only in the limit of infinite amount of random nodes, and if you have some limited amount of them, for some finite amount of them, as you always do, then it will be only some kind of approximation, and you don't have any control over how accurate this approximation would be. Then there is a very promising method of Goombahs of Max Relaxation. Basically, you replace your random variables with a softmax that is perturbed with Goombah noise, and it has some good properties that if you use hard argmax, the discrete operation, then you will exactly recover the discrete random variables. However, argmax is not differentiable, so you replace it with a softmax with the temperature that approaches the argmax as your temperature goes to 0. So you can set some non-zero temperature and hope that it would work okay. A nice benefit of that is that if your temperature is sufficiently small, like less than 1, then your modes are likely to be on the edges of your simplex, so that the hard values, like 1 and all other values are zeros, would be the modes of your distribution, and hopefully you will be sampled more often than other points, and that would be leading your network to your weights to adjust to these points, and this is exactly what you'll be using at the test time. That's a good thing to have. However, all these relaxation methods are biased, and in this case it's not clear how to actually tune the temperature. Can you always have it fixed to some value like 0.4, or do you actually need to tune it, or need to cross-validate it, or maybe do you even need to have some annealing schedule? It's kind of complicated. There's also a family of methods for those who who hate mathematics, and well, I already saw about it. I don't like these methods. Okay, so there was an example showing how good these methods work, and that the Goombahs of Max seem to be working better than any other methods, that I used for the comparison. Okay, so now let's move on to the new material, and I guess I'll mostly use the whiteboard. So recall that we actually had a very general method called the reinforce, and I'll derive it once again. If you want to obtain the gradient of your objective, that is average of some target function averaged over some distribution, you can do the following. First, we write the expectation as the integral. Then we move the differentiation inside of the integral. The target function does not depend on theta, so it's just this quantity. Then we notice that actually, if you differentiate that, I jumped fast. Then we notice that actually the gradient of a logarithm of the density is the gradient of the density itself divided by the density. Plugging this in, we get the following. And this is exactly the expectation of f at z times the gradient of log density. We already seen how having strictly positive f can break your estimator, because all the directions will have positive values, and you only can hope to obtain good gradient estimate if you average many samples from this distribution, so that the good ones would outweigh the bad ones. So one thing you could actually try to do is to subtract some baseline from f, some constant that would center your reward, your target function. Well, in general, let's think what we could actually want to do, what we would actually want to do to improve this estimator. Well, at first we would like to our target function, something that we want our weights that now are represented by our target function to be positive for good directions and negative for bad directions. So one way is to just subtract some constant or some other baseline that would tell us how good or how bad our specific sample z is. Ideally, what we would actually want to do is to subtract something that might depend on sample as well. That would zero out this gradient at all. Of course, by subtracting something that depends on z, we will introduce bias into our model, and we would have to fix that by adding the gradient of the expectation of f at z. I mean, clearly, if you move this thing out by reversing this argument, you can see that this addend is just this expectation, the gradient of this expectation. So if your expectation is 0 and you're if you're subtracting only a constant, then this would be a constant as well. This would be just 0 addend. Of course, that would not get rid of this term completely. That would only center it. However,
but it will reduce the variance already.
Yeah. Well, it depends on how you choose the constant. Yeah, but the general idea we'll follow is that we would actually probably want to approximate this function as good as we can, so that the influence of this term would be as low, as small as possible. Yeah, and there are some benefits of the reinforced. That it's very general. It can be used to obtain sparse gradients, where you only need to, well, it's something that I call sparse gradients. This is what we want, what I just covered. Yeah, this thing is usually called control variate. Okay, let's see some specific cases of control variates. One control variate that was introduced some time ago was actually copied over from the reinforcement learning literature, because in reinforcement learning people have been using these methods called policy gradients for quite some time, and they came up with some efficient variance reduction techniques. Here I will assume that your random variables z depends not only on theta but also on some auxiliary input x. For example, you can think of this as doing variational inference, and your f of x and z would be evidence lower bound. Oh, yeah. The expression that is under the expectation in evidence lower bound. Then, if you actually have this kind of extra information, you can make the baseline dependent on x and also subtract some additional constant baseline.
So you mean if the distribution with respect to which you would like to differentiate also depends on some additional parameter?
Yeah, you can include that
Yeah.
as well.
In baseline.
Because why not? You can only do better by doing this.
And I think that this makes sense mostly for amortized variational inference, right? When we're using some kind of, say, neural network.
I guess, I mean, the main application of these ideas that I know of is, of course, variational inference. So, I mean, in reinforcement learning as well, people have this extra information called state.
Mm-hmm.
There, x is your current state. So, yeah.
And then now the process to switching to deep neural networks. Again.
Okay, so
this is pretty clear that the baseline can depend on x as well, since we integrate with respect to z.
yeah, the only question is how do we actually tune the baseline?
Right.
And in these methods, authors propose to tune the baseline by minimizing the following quantity. It's very well known that if you are minimizing something like this, then at optimum, the optimal B would be the expectation of your target function. In reinforcement learning, this would lead you to having value function as B, and well, the F would be your Q function. Actually, I suggest you to remember this formula, because we'll see that it might be not the best option actually, and in later works there is well, you can directly minimize the variance of the gradient estimator. You can directly minimize the variance of all this thing, And it's somewhat related to this formula, but not exactly. We'll see how they differ. In the same spirit, you can obtain good value for C, and there is actually not much sense in writing it as a separate argument. Just in neural networks, you typically have some regularization on weights, and it might be not easy to model arbitrary bias for your outputs. Also, in this Anvil paper, authors proposed some other tricks to make the learning more efficient. One of them is variance normalization. They divide the gradients by the estimate of standard deviation. This is actually what this is what good optimization methods do for you. For example, Artem does that for you, so you don't need to worry about this point. And the third one is also well known for people doing reinforcement learning. The idea is that suppose you have layered structure, you have some stochastic layer Z1, then you have stochastic layer Z2, then you have stochastic layer Z3, and so on. In reinforcement learning, those stochastic variables are actions, and the next action only depends on all previous, only through the last one. So in that case, typically your reward, your f, the target function, can be expressed as sum of rewards for each stochastic variable. Then you can write the objective as following. Obviously, this is an expectation of a sum of targets for every random variable, for every layer. Each is multiplied by the gradient of log density. Then, if we represent this gradient as the sum of gradients for every stochastic layer, we'll actually have here an expectation or sum of all pairs and we can see that if k is not equal to n, then the corresponding expectation would be 0, because those samples are in the well, okay, it won't be quite 0, because so if
I think it will be 0 because you can like...
No, it will not always be 0. It will only be 0 if k is less than n, or n is less than k, let's see. Because your action at the because your stochastic layer n depends on previous layers and x. So yeah, if your k is bigger than n, then essentially you are taking an expectation of something that does not depend on example, you're taking expectation of something that is constant with respect to the square function.
Okay, briefly speaking, we may simplify this expression, right?
Yeah. In the same way as in reinforcement learning, people simplify their objective, the same kind of objective, saying that future rewards for future actions do not depend on what we have done so far. If we're taking some action, then previous rewards do not depend on this action because we cannot affect the
Future
past.
actions do not influence to the past
Right.
rewards. This, yeah.
And the same will be acquired here. The future z would not be influenced by previous rewards, previous target functions. But this is only for f of special kind, of special structure, but this applies to random models like this, to these layered random models. There is also a quite powerful generalization, well, not quite a generalization, but a related method that is called VIMCO, the variational inference for Monte Carlo objectives. However, I do not cover it here because it's very specialized. I mean, I only can think how to apply it in the variational inference scenario. And here we are considering a bit more general case. However, it seems to be very efficient in practice. So if you are doing variational inference, I suggest you to look into these methods. The downside is that the variational inference for Monte Carlo objectives requires you to have many samples of your, it requires you to have many samples and compute your target at many points, which would probably increase the training time, increase the computation time proportionally. Okay, that was the angle estimator, quite basic actually. It didn't use any information, it didn't use the gradient information about f either, so maybe we can do something to actually do so. Okay, there was an idea of a new prop estimator, and the basic idea is that, okay, we talked about what do we actually want from baselines. We want them to approximate our f as good as possible, and one way to do so is to consider a Taylor expansion of your f at some point. So this time we consider the action-dependent baseline, the sample-dependent baseline. We'll say that f hat, f tilde, the approximation we'll use as a baseline is actually f of zeta plus the gradient of f zeta times zeta minus zeta. So this is linear approximation. However, it uses the gradient information of your target function.
Excuse me, it should be the other way around, z minus zeta.
Right. Now this is action-dependent baseline, so it no longer has mean zero. However, we can actually compute the bias that is introduced by using this control variate and fix for that. In particular, our gradient would be f at z minus f at z, the baseline, times the scar function, plus we'll need to add this thing. Now, by reversing the process that we have gone through, like here, of deriving the square function, we can see that
It should be 0, no?
no, it depends on zeta, so it is not 0.
But it's leading function,
Yes.
so okay.
So this is actually the gradient of the approximation. So since this is not a constant anymore, the gradient would not be a constant also. However, because of the simple form our approximation has, we can actually compute, in most cases we can compute this expectation analytically. Say that this is this thing.
Why so?
Because of linearity of everything. Everything is linear. All we need to do to actually apply this method is to be able to compute analytically compute the expectation of our random variables. And usually...
And the derivative.
Yeah, and the derivative... Well, yeah, and then differentiate through, but that's usually...
So if you compute the expectation analytically as a closed form function of theta, then only differentiate it easily.
Wait, but don't you have, like, if you, in the first form of this expectation, if you write down f of xi, right, plus something,
Here.
this f of xi doesn't depend on z, right? So this term should be 0.
Yeah, right. This one... yeah, this one is actually 0 once you differentiate it.
Okay.
Is that what you are talking about?
Yeah, I guess so.
Okay, so now the question is how you actually choose the zeta. How do you actually choose a good point? And the authors suggest that you just use the mean version of a network. It is to say that zeta that corresponds to some z is just an expectation of that z. So if somewhere in the network you have a binary Bernoulli random variable, you assume that zeta here is just the rate of that Bernoulli random variable, and the z itself is, well, the Bernoulli random variable. Okay, so...
But then, won't it happen that expectation of z would be equal to xi, exactly? And we'll modify the second multiplier.
I think xi is fixed, and expectation of z is like smoothly depends on the parameter.
So we do not compute xi. We just fix xi.
Psi is obtained using the mean version of a neural network, where each stochastic node is replaced with its expectation.
Maar we don't backpropagate through data.
We do not.
We do not. This is already a gradient expectation. We don't need to compute any other gradients.
Mm-hmm. Okay.
Okay, this method already uses some gradient information. However, it uses only first order approximation to the target function. And in order to minimize the influence of the square function, we would like to approximate the target function as good as possible. By now we already know that there is a powerful method of Goombahs relaxations that can probably approximate the Target function, the discrete random variables, and the random function, and the function of these discrete random variables quite good. So let's try using that. This is the idea of the method called rebar. This time the baseline would be a relaxed version of the same stochastic computational graph. This will say that f tilde is, well, something that approximates the, okay, so we'll introduce zetas that are actually continuous random variables, the relaxed versions of the corresponding z, and we'll try to find such zeta such that the f evaluated at these random variables would be as close to f as possible. That's what we will hope for. So one way to do so is to notice the following. We can re-express any Bernoulli random variable in terms of a non-differentiable transformation of uniform random variable. That is, if you sample a uniform random variable on a 0-1 interval, then it would have the same distribution as our Bernoulli random variable. As we learned in previous talk, there is no need to use only uniform random variable. For example, well, actually, most of the time you want to use random variables with infinite support, and the good choice are logistic distributions that are a special case of Goombahs that are obtained as a special case of Goombahs relaxation. So assuming that X is a logistic distribution, then in order to obtain the discrete random variable with the Bernoulli distribution of parameter p, you need to compare to the logarithm to the log odds, essentially. So that means that our score function can be written as follows. Probably mine is here. Let's say that X is logistic with mean log pi over 1 minus pi and the standard deviation 1. Then the square function estimate would be written as follows.
And the expectation is computed with respect to continuous variable x.
Yep.
So we had an expectation with respect to discrete variable, and instead we now converted it to expectation
Yeah.
with respect to continuous variable.
So far we
But from
we did
non-differentiable function.
representization, right? But we introduced the non-differentiable function in our computation graph, so we cannot. Well, that didn't give us anything. One way to introduce a baseline here is to actually subtract f of sigma tau x gradient log density. However, that would be an inefficient estimator because here we sample x with a big support, and if we were using discrete version of reinforced estimator, the one with the discrete random variable here, that would be essentially marginalization of this thing with respect to x. So you will not sample all the all the possible variables, all the possible values of x, but only those that lead to different outcomes, to different binary outcomes. And so what we would actually like to do is to re-express the whole thing as in terms of binary random variables, in terms of the z's, not x's. Is that clear? Or
No. You should provide with a bit more details. So we have discrete variable z. We have a continuous variable x. We may compute directly z given x.
right?
This is deterministic equation, but not vice versa.
Mm-hmm. So in this mapping, when you map, well, there is, if you have x, you can uniquely determine z.
Right.
But it's not the other way.
Mm-hmm.
So you can expect the variance to increase if you working in the x space.
Because we add some more variance. Yeah. So
what we would actually want to do is to go back to z's and work with them, so that our score function would be not this thing, not this guy, but instead the gradient of the log density for the discrete case.
So how can we do that?
Well, we need to somehow re-express this thing in terms of well, we need to marginalize this thing over random over z's. Let me show you.
So this is expectation with respect to x, but we may rewrite it as follows: as expectation with respect to z and expectation with respect to x given z.
Mm-hmm.
Right?
Yeah. So imagine you have the expectation of this baseline is given as via this formula. You can add the z here because well, it already essentially right this way because this guy is already a constant.
But then the inner expectation is conditional. Expectation with respect to x given z.
Well, okay, let's just write it with respect to the joint.
Okay.
Okay, then we can rewrite it using the conditional.
Oh, this is exactly what was written here. So the outer expectation with respect to z, and the inner expectation is with respect to conditional x given z.
Mm-hmm. So, yeah, we move out the differentiation. write the inner expectation in the changeable way. No. So, square function this time, because we moved out the differentiation. Now we move the differentiation back in, and well, this thing depends on theta in two ways. First, it depends on theta here, then it depends on theta here. So there will be two addends. First one is the differentiation of the inner function. And the second is the square function for the outer expectation.
And what's the profit?
And the profit is that we'll be actually using this thing as a baseline. It depends on the, well, this would be a baseline, and this is the marginalized square function.
And this baseline actually has very high variance, just like reinforced estimate. But this variance is highly correlated with the variance of initial stochastic gradient. And if we are using it as a baseline, we'll compensate the high variance, right? So that's the idea.
Yep. So now if we, let me use a different color. So what we now do is we okay, so we differentiated this double expectation expression, and it depends on theta in two ways. First, the expectation itself depends on theta, and then the inner expectation is a function of theta. So when we differentiate that, we need to have two addends, one with respect to the outer expectation, that's the second one, and one with respect to the inner function, that's the first one. If we continue to work in simplifying this term, we would obtain a square function here as well. However, we actually can reparameterize this thing.
And the second term, why we remove f function?
Yeah, I forgot about it. It's correct observation. Okay. So
The first term will be exactly Goombahs of Max Relaxation.
not quite, because here x is not any variable but a conditioned one. So here you will not sample you will not sample marginal logistic distribution, but you will sample only the part of logistic corresponding to one branch of your binary random variable. That's
So, in order to compute the first term, we will sample z and after it to the conditional distribution of x?
We'll see in a moment. So the expression for the gradient can be expressed this way. This is the random variable x that is conditioned on z, and z is h of x. Well, essentially, this is z. This is our baseline score function. And now we need to compensate for the bias. In order to do so, we use this formula that actually says that, well, this is the gradient of a reparameterized version, of a reparameterized expectation. The Goombahs of Max Relaxation. This time x is not conditioned on anything. And, okay, yeah. So the expectation of our baseline is the gradient for reparameterized version minus the gradient of a conditionally reparameterized version. Now we can merge these expectations together. Yeah, well, also we can multiply the baseline by any constant we want.
So everything that we have multiplied by eta has zero mean, right?
Yep. Well, if you leave only those,
Yes, only
then
those.
the expectation, then it will be zero. Yeah. So now you can re-express the following using just two uniform random variables, u and v, uniform on 0, 1. You can use those to obtain, you can use u to v, u to y, u to obtain the logistic distribution with a specific mean. You add theta along the way. Then you can use this to obtain both discrete version by applying the Heaviside function as well as the relaxed version by applying the sigmoid with temperature, or softmax for that matter. And you use v along with z to obtain, and well, theta as also, to obtain x given z. It's also easy to write down formulas for the corresponding branch of logistic distribution.
So can you explain in what sense this conditional exists? Like, what is x given z? Like, how do you derive this formula at all?
Yeah, well, you can derive it using the Bayes rule, where essentially you have a deterministic model for z given zeta. If you have well, z is just h of x. That means that your likelihood of z given zeta is singular distribution. Well, okay, I guess it's easier to just look at the density. Your x is a logistic with a unit variance and some shifted mean. So its density, its CDF will look something like this. Then you can see where it crosses the 0, and depending on z, you choose either this branch or this branch, and then you can sample from these branches by sampling uniform distribution from 0 to that point, and applying the inverse CDF the corresponding value and the corresponding sample.
So this means that everything seems to be pretty computable, right? And what's the advantage? Do I understand right that we eliminate the bias caused by Goombahs relaxation by generative bar?
Right.
Because Goombahs relaxation is, well, generally speaking, is a bit biased estimate. Probably the bias is not that big, but still it exists. And rebar allows us to eliminate it completely, to get absolutely unbiased estimate for the true gradient.
Right.
Although, well, my deep feeling is that actually this is not necessary, because the bias is quite tiny. But this is mathematically correct procedure.
Now, if you look closely, you can see that there are two parameters, namely eta and tau, that are not obvious how to choose. Okay, of course, you can treat them as a hyperparameters and then just tune it in a cross-validation or some kind of Bayesian optimization procedure. But actually, you can learn them in a principled way, because all we want to have is as low variance as possible, and you can minimize the variance directly. You can optimize these values eta and tau to minimize the variance of the resulting gradient estimator. Suppose that g hat is your estimate for the gradient, that formula in the second row, and we'd like to minimize the variance of each component of that estimator with respect to tau and theta, tau and eta. By the way, question to the audience: do you know how to come up with an unbiased estimator for the variance if you don't know the mean or don't know how to compute it?
No, but can we use empirical mean?
No. It will be biased estimator, of course.
Well, we will be able to eliminate this bias.
You are only allowed to use one sample, and
You want us to get an unbiased estimate for the variance by using one sample?
right, exactly. Well, okay, 2 samples. But for 2 samples, the bias that you introduce by using some function of empirical mean might be too high.
Right.
So the question is the same. Can you write something? Well, okay, what we want? We want some j of z such that its expectation is the variance of j I of Z. Any ideas?
Like square minus function, the regular usual formula for variance.
Like this?
Yes.
Yeah, but how do you estimate this one? You can't just use empirical estimate for this expectation, because well.
But like, if you cannot use empirical estimator for this, then like it probably means that you cannot use empirical estimator for anything else. Because what can be simpler than this?
Oh, there is a very simple trick. Namely, well, this expectation is just a product of two expectations. Now let's use two independent samples for this.
But then we don't need an expectation anymore, because we only have two samples, according to your problem formulation.
Yeah, and those are two samples we'll be using.
But there's no expectation.
Wait. So what we want to have is some unbiased expectation in some unbiased estimator of the variance, and that would look. The J here is this unbiased estimator. So the J that I'm proposing would be, well, z square minus z1, z2 for two samples.
Why not 3?
So if you are sampling 2 times from the distributions, why not just like using those like everywhere?
If you put here two sample mean, two sample estimate, the resultant expression would be biased.
Yes, but you can make it better by using two samples in the first expectation.
Yeah.
Like take half of z1 squared plus z2 squared.
Right. Is it possible? Probably we shouldn't get any bias from that.
Okay, let's leave it to the after talk discussion. But I believe that would not give you an unbiased estimator.
That sounds quite strange.
Maybe.
Because from symmetry conditions we may write down the similar expression but with the z2 squared as the first term. And it will be unbiased as well. And then if we average the two, we'll still get unbiased estimate, but with lower variance.
Right.
So probably we can't do that.
But that would be a full square.
Sorry?
That would be will be the full square of the difference between Z1 and Z2.
And this means that when we use simply the difference between the two samples, the square difference between the two samples.
It will have like.
And this is quite natural and quite reasonable. So probably. Yes.
The previous expression that you had, isn't it just unbiased estimator for the variance with the mean, like something squared, something minus mean squared?
Yeah, but if you use empirical estimator squared, that would no longer be an unbiased estimator for the.
No, I mean the expression that you had, like expectation squared minus expectation of squared, is you can re-express it perfectly, like 1. In that form, like n divided by n minus 1, something like that, times something in squared, like the regular estimator for the variance. You just open the bracket.
Are you sure?
No, I introduced a second sample. You can't express the variance using only one sample.
No, I mean variance using 2 samples. Unbiased estimator for
Okay.
regular.
No, actually, the expression can be written as follows. So we simply take z1, z2, the difference, square difference, and divide it by 2. So this is it.
Maybe.
And this is the same expression we get if we use standard formula for.
No. The standard formula is like sum and then zi minus the mean.
There's no
And that
two terms.
expression is exactly that you read.
Right? So this is what you're talking about,
And divide by 2.
and divided by 2.
No, by one.
Yeah.
By one.
By one, yes. Because n minus 1.
Makes sense.
So,
This is exactly that estimator.
that estimator.
This
These are the
is exactly the
equivalent.
estimator of
Okay.
Artem.
Anyhow, this was a tutor that is irrelevant to what we are talking about, because in our case we have an unbiased estimator of the gradient, and we want to optimize with respect to tau and eta that do not, since this is an unbiased estimator of the gradient and the true gradient does not depend on our baseline, it does not depend on eta or tau, so the expectation of this thing does not depend on these parameters at all. That means that our variance with, in terms of eta and tau is proportional to the square of each component. And essentially minimizing the variance, we are minimizing the square. So we want to minimize the variance along all the coordinates. This can be essentially re-expressed as the sum of fz minus well, okay, let's not worry about this. So you can estimate this quantity by just sampling random variables as usual and minimizing the gradient with respect to tau, with respect to eta, with respect to eta and tau. And actually, so this looks like a very good improvement of the Goombahs of Max Relaxation that gives you an unbiased estimator and a way to control all these free parameters, eta and tau, that we didn't have control over, didn't have a way to automatically adjust in the basic Goombahs of Max Relaxation. The downside might be the need to sample 3 random variables, namely the discrete random variable, the conditionally relaxed one, and the marginally relaxed one. However, well, that's the price you pay. You can actually take this idea even further. That was the last week's paper, Backpropagation to the Void, from the Toronto lab. Where they said that, okay, so here we already learned some part of our baseline minimizing the variance. Why not learn the whole baseline minimizing the variance? What if you are doing reinforcement learning and you don't have access to F? So you can't just relax it easily. What you can do instead is to use some kind of different neural network as an approximation to F, and learn it by minimizing this criterion, this estimator of the variance. For continuous random variables, you can use the usual representation trick, and for discrete random variables, you minimize the variance. So that's it. Thank you for listening. I already showed you this slide last time, so any questions?
The better technique still remains, I'm afraid, unclear for the most of the audience. But no, it's really quite difficult to understand it from the first glance. So any questions?
Yeah, I think the main question is, as usual, like, why do we expect this kind of baseline to work? Because at this point, like, all the baselines except maybe this optimal baseline technique, which is pretty much intractable. All of them have this question like, why do we expect the variance to decrease if we choose this particular baseline? So there is no good answer to this, I'm afraid. Maybe Artem has something.
Well, if you are lucky.
Yeah, I mean, when you choose any baseline, you just say, if I'm lucky, then it will work. Otherwise, I will just set the constant eta to 0, right? So.
Yeah, right. If you're lucky, this thing approximates the relaxed version, approximates the discrete one as well as
Moreover,
possible.
with eta equal
Yeah.
to 1.
If you're lucky, it approximates. Well, these two quantities are basically equal, and the reinforced term goes away at all. And all you are left with are usual reparameterizable terms, fully reparameterizable.
Yes, but what is this difference of the gradients for two models? Like, what does it even correspond to? Can it be that it would have like higher variance than the original relaxed model?
Well, since you tune the eta, then you always could put it to 0, and
I think they approximate the variance of the result and then prove that it will be like this approximation will be better, and then they try to tune the eta to like make this approximation better. So in some sense they in some loose sense they do prove some that it is better.
That's still unclear because Goombahs of Max Relaxation is some analog of reparameterization trick. And reparameterization trick has the lowest possible variance of stochastic gradients. So probably it's
well,
impossible
you
to
can
do
always reduce the variance even further. So, do you have any proofs to back your claim about the lowest possible variance?
There was some paper which claimed that it is not possible to reduce the variance even more.
Can they prove anything, or was it pure experimental?
I guess they proved something, but I'm not sure.
But they
But
don't
well,
claim.
this seems to be quite intuitively clear, actually.
Well, you can always take more samples and reduce the variance.
Yes, sure. By taking more samples, you can. But not by performing some kind of mathematical derivation. And if so, then Goombahs of Max probably has the lowest, or closely the lowest possible variance for the discrete variables. The only problem is that is in the bias. So here we are eliminating the bias, but I don't think we can guarantee that we may significantly reduce the variance. So mostly what we do, we're trying to eliminate the bias. And it may happen that the price to pay will be the increase in variance. Because we no longer make a reparameterization trick, or analog of reparameterization trick. We add some reinforced components.
Well, here this is the term for the Goombahs of Max relaxed model. So as you can see, there are some additional add-ons, and there is indeed no reason to hope they will contribute negatively to the total variance. So I would rather see it as an improvement over the reinforce rather than improvement in the variance, in the sense of variance of the Goombahs of Max reparameterization.
Okay, or equivalently, as a way of removing bias in Goombahs of Max Relaxation.
Yeah, well,
Because it doesn't provide us with an unbiased estimate, strictly speaking. And this estimate does.
Yeah, I'm almost sure that this thing will have worse variance than Goombahs of Max and better variance than the original reinforce. So it's like straight up, right?
It should have better variance than reinforce. At least we were not silly with the selection of eta. And well, unfortunately, probably you're right, that it will have larger variance than Goombahs of Max.
yeah. I guess I'd like to also tell a word or two about the variance minimization. So in this relaxed paper, authors said that okay, if you even know the function, you can still, maybe it's not optimal to use the same f, but maybe it's worth to somehow alter it and add the baseline some more flexibility. For example, they added a small neural network that added some additive value, and the idea is that okay, so when you're minimizing the variance, it is minimized when you're relaxed when you relax the computational graph strictly matches the discrete one. However, in the meantime, it's not always minimized when you... So remember that in Anvil, we minimize the expected square difference between these two. And this probably was not the best choice in terms of the variance of the whole gradient.
Oh yes, the minimization of squared term was in some sense, well, this is simply using conditional expectation, just like we do with the constant baseline. The heuristical choice of constant baseline is to choose expectation. But there's no guarantee that this is the best possible constant baseline.
Yeah,
The
so
same
what I'm trying to say is that actually you could use the same idea of variance minimization in order to optimize the baseline in the Anvil here. Instead of minimizing the square difference, the expected square difference, you could minimize the variance, and probably that would lead to better baseline.
Yes, it can.
Maybe I'm saying something stupid, or maybe you mentioned it somewhere, but can you train a neural network to trying to approximate the reinforced gradients, and then use this neural network as a control variable, which will be biased, but like which will make sense, right?
I guess you could. The only question is how would you fix for the bias that this network introduces? You would need to compute the expectation.
Makes sense. But you probably can.
Well, this is close what people in Libar are doing, in the Relax doing, except they don't. They only adjust the scalar that. They don't adjust the vector component of the baseline. They only adjust the scalar component.
But you can still do kind of like tailor approximate your neural network and then use it, right?
I also think that you can do something really interesting if you take the idea of synthetic gradients, where you don't actually do where you have a neural network which gives you the gradient for your current variable, right? Like bypassing the backprop, and then you actually try to train it using the reinforced gradients.
I think that's like exactly what they just said.
Yeah. So.
Yeah, but the same problem applies then. That how can
No,
you compensate for the bias?
You can't compensate for the bias, but this, like, if you somehow would still be able to do backprop there using these synthetic gradients, then you would still have proper backprop, but you would also have some guarantee that in the limit when you have a lot of reinforced training data, you would get the proper gradients. So, like, if you say that you do 10,000 passes of reinforced to train the neural network for one update using the just backprop, then maybe the bias will be very low.
Interesting thought.
Any other questions? Okay, well then, thank you for your attention.
Yeah, let's thank the speaker. And, I suggest to move the next talk in 1 week. Sorry?
There is already a talk.
Well, our next speaker should be Pasha. Where's Pasha?
No, the next speaker is a near information Bayesian approach by Artem.
Yeah.
Okay, so maybe we'll move you up in 2 weeks. Okay.